Hey guys, so next lesson is going to be a review on 16.8 where we are still solving linear equations, but now we're talking more about the nature of the solutions. So we're going to solve and then we're going to determine whether the equation has one solution, no solution, or many solutions. So up until this point, every equation we've solved has had a solution. Moving forward in this unit, that's not always going to be the case. So this first three examples that I go through are going to be just showing you algebraically how you determine whether something has one, none, or many solutions, and then I'm going to pull up the vocab, and that will talk more about graphically and by looking at the equation. Okay, so we're still solving as normal using the same success criteria. So I'm looking at number 1 and I'm saying to myself, do I need to use the distributive property? And I do, so I'm going to go ahead and do that, distributing this -3. Okay, once I do that, I have -3 minus 18x is equal to 14 minus x. Okay, and just as usual, I'm going to combine any like terms on either side if I have them. In this case, I don't, so I'm going to move right on to getting x by itself, which means I need both of these x's on the same side. So I'm going to start by adding x to both sides. Okay, when I do that, negative 18x plus 1x gives me a negative 17x. And then I'm just left with 14 on the right. Okay. Now I'm trying to isolate x, so I need to move this -3, and I move a -3 by adding it. Which leaves me with negative 17x equals 17. But that x is not alone yet. I need to get rid of the negative 17 in front of it. And remember, when you have a number up against a variable, that means you're multiplying. So to undo multiplication, we divide. Okay, so x is equal to -1. Okay, whenever you solve something algebraically and you get x equals a number, that means you have a solution. You have one solution. And that solution is -1. That's the type of problem that we've been working with so far. Now the next two are going to be different. So we're still going to tackle them the same way. We're going to start and see if we need to distribute. And in this case, again, we do need to distribute. We have a 12 to distribute and a 4. So I'm going to go ahead and do that. Okay, 12 times 2x gives me a 24x. 12 times 11 gives me 132. Distributing the 4 on the right, 4 times 6x gives me 24x. 4 times -9 gives me -36. My second success criteria, can I combine anything on the left side or the right side? And I can't, I don't have any like terms on either side of the equation. So I'm going to move to success criteria 3 and start using my inverse operations to solve. So since I'm trying to solve for x, I'm going to get my x's on the same side by subtracting 24x from both sides. Okay, and you'll notice that that cancels out on the right, but not only does it cancel on the right, we also have 24x minus 24x on the left, which also cancels out. Okay, once that cancels out, you do not have an x anymore. It's gone. So you are left with 132 equals -36. Okay, 132 does not equal -36. It will never equal -36. This is a false statement. And when we have a false statement, that means we do not have a solution. And you can even put a little slash through that equal sign because 132 does not equal -36. Okay, last type that we're going to look at is number 3. And we are still going to follow the same success criteria. So distribute if we can, which we can. We have a 5 to distribute on the right. And when I distribute that 5, I get 5x plus 10. I still have that minus 7 on the right. Can I combine any like terms? Well, 3 and 5x are not like. On the right-hand side, I do have 10 minus 7 that I can combine. So let's do that. Now I have 3 plus 5x equals 5x plus 3. Okay, start solving. I want to get my x's together on the same side, so I'm going to subtract 5x. And you'll notice that it cancels out on the right and also cancels out on the left. So what I am left with is 3 equals 3. 3 does equal 3. 3 will always equal 3. So that is what we call a true statement. When we solve and we get a true statement, that means we have many solutions. So those are 3 examples that have been worked out for you algebraically. Now I'm going to pull up the vocab page and we're going to take a look at what one, none, and many solutions look like on a graph and also in a table. Okay, so here we go. So if we're looking at a graph, we know that the solution to a graph is the intersection point. So if I look at this first graph, we have an intersection right here at -1, 1. The lines intersect. That means we have one solution, and that solution is x equals -1. If you look at the second graph, the orange graph, we have 2 equations that we're solving. 2x plus 1 equals 2x minus 4. Those lines are parallel. They have the same slope, different y-intercept. So I'm going to write that here, same slope, different y-intercept. That means they're parallel, which means they never intersect. And if they never intersect, we have no solution. Okay, last one, if we had the equation 2x plus 1 and 2x minus y equals -1, if you were to rearrange this, this second equation would be y equals 2x plus 1 as well. So those are the same line. Okay, when you are looking at a graph of 2 different equations and you have the same line, that means that they intersect at every single point. So we have many solutions, so they intersect everywhere. Algebraically, we just did 3 examples algebraically, but you can see again, as you look through here, you get x equals -1, and that's our solution. Number 2, you can see again, we have 2x plus 1 equals 2x minus 4. If we were to solve algebraically, you would get 0 equals -5, which is not a true statement. 0 does not equal -5. So that is a false statement. And then example 3, if you solved, you would end up with -1 equals 1, which is a true statement, and true statements mean that you have infinite or many solutions. Okay, the last thing that we want to look at is a table. Okay, tables are a little tricky, but we can still address them. So if we have 2 lines that intersect, if we have an equation that has a solution, we can identify that in a table. So if you look at this table in this pink box right here for one solution, we are looking for the x value where y1 and y2 are the same. And you can see here that at x equals -1, y1 is 1 and y2 is also 1. So there's your solution, x equals -1. If you're looking at a table like table number 2 and you don't see the intersection in the table anywhere, it's a very good idea to look at the slope. So if we look at the y1 column, that would be our first equation, or our equation on the left-hand side. 1, 3, 5, 7, those are all increasing by 2, plus 2, plus 2, plus 2. That means our slope is 2 over 1 because our y's are changing, or our x's are changing by 1 and our y's are changing by 2. So 2 over 1 gives me a slope of 2. If I look at my y2 column, which would be my equation on the right-hand side, -4, -2, 0, and 2, those are all also increasing by 2. So that means that y1 and y2 have the same slope. Okay, so they have the same slope, which is 2, but they have different y-intercepts. How do I know that they have different y-intercepts? Because in the table, y1 has an intercept of 1, and y2 has a y-intercept of -4. So same slope, different y-intercept means that they are parallel and never intersect. Therefore, they have no solution. Okay. A little easier to see in a table when something has many solutions because you literally have the exact same information in y1 and y2. So those are the same line, which means they overlap in every point, which means they have many solutions. Okay, guys, quick little review on this. Still continuing our work with solving algebraically, but also bringing in the graphing and the table at this point. So everything will be posted. Good luck.